Physics just confirmed the universe is cheap, the cosmic energy lie. You think reality's infinite, smooth space, endless detail, perfect resolution. It is. Physics says the universe runs cheap, hard caps, speed limits, and an irreducible hiss that never goes away. Here's the simple truth. Energy and information are the same currency, and nature spends it sparingly. I'll show you the receipts, Shannon's bits, Landauer's heat bill from the 196s, Bekenstein's area limit from the 197s, and a test that could break this story. If reality is optimized, your senses are compression artifacts. To see the lie, we start where energy meets information and watch the ledger snap into focus. Energy is information. Shannon, Landauer, Bekenstein. Okay, so basically, if information has a physical cost, then perfect precision is never free. Claude Shannon, working at Bell Labs in the late 194s, gave us the math of information, bits as choices, entropy as uncertainty, and channel capacity as the maximum choices per second you can reliably send through a noisy pipe. That was the blueprint. But the moment you ask, what does 1 bit cost in the real world? You slam into heat. Enter Rolf Landauer at IBM in 1961. Landauer's principle says erasing 1 bit, forcing this, not that, dissipates at least kT ln2 of heat at temperature T at room temperature. That floor is about 2.8 to 3 times 1021 joules per erased bit. Tiny, but crucially not 0. 0 would be the only number that makes infinite precision free. This is the receipt computers can't dodge, and neither can measurements, memories, or any physical process that overwrites alternatives with a definite outcome. Think of it like a pay-per-bit universe. Every time a system commits to yes over no, some energy is pushed into the environment as heat. No free deletes, no perfect resets. If you wanted flawless fidelity everywhere forever, you'd need infinite energy into an infinite heat sink. That's not physics, that's fantasy. Here's the weird part. We talk about computation as something laptops do, not what the universe does. But measurements, memories, and state updates are logical operations with thermodynamic footprints. Maxwell's demon, the mythical cheater of the second law, gets caught at the memory line. To erase its notes, it pays Landauer's bill. Nature's accounting is boringly consistent. Now zoom out. Jacob Bekenstein in the early 197s asked how much information fits in a region before gravity answers no. His bound says the maximum information scales with the area of the boundary, not the volume, for given energy. Push beyond that, and the region collapses into a black hole. The Bekenstein-Hawking area law then says a black hole's entropy equals its horizon area divided by 4gh stroke. Translation: the most data you can store is written on the surface in Planck-sized pixels. Area, not volume. That's compression logic at cosmic scale. Everything clicked when I stacked them. Shannon tells you what bits mean for uncertainty and communication. Landauer sets the energy cost to commit or erase a bit. Bekenstein caps how many bits fit in a region for a given energy and size. Together they scream, detail is rationed. There's a spend to decide, a ceiling to store, a bandwidth to send. Let's make it concrete. Try to describe a tiny cube of space to absurd precision, every field value with infinite decimals. Shannon says that's a huge information payload. Landauer says committing those digits costs heat per bit. Bekenstein says before you're done, gravity collapses your cube. Infinite detail either cooks your lab or makes a black hole. Precision is a luxury. Okay, so what this actually means is straightforward. Computation equals heat. Memory equals mass, energy, and area. Communication equals energy transport. If you want reliability, you add redundancy, more bits, which increases storage demand and energy cost. A universe that wants to run fast and not implode learns to be thrifty. Compress what's predictable, defer decisions until necessary, and only pay for precision where outcomes hinge on it. Wait, what does this show up outside thought experiments? Absolutely. Your phone throttles because compute makes heat. Your brain forgets because retention costs. Your best detectors hit quantum and thermal floors because extracting certainty costs. The confusion we inherit, that nature should reveal infinite detail on demand, dies when you accept that bits have bills. Credibility markers. Here's the lineage. Shannon's 1948 mathematical theory of communication defines bits and capacity. Landauer's 1961 IBM memo, later formalized, sets the thermodynamic cost of erasure. Experiments since the 200s have measured it near the KT-ln2 limit. Bekenstein's 1973 bound, sharpened with Hawking's 1974 radiation result, ties information to geometry. These aren't edgy takes, they're pillars. Micro story. I once explained Landauer with a recycle bin. A friend said, "Can't we just overwrite without erasing?" I said, "If you don't know the old state, overwriting is erasing. If you do know it, you paid to know." She paused. "So there's always a receipt." Exactly. Heat, measurement effort, or gravitational constraint, the ledger always closes. Holographic hints reinforce the thrift. If black holes encode microstates on surfaces, not volumes, nature's most extreme data vaults already run area-based storage. That's not mysticism, it's economy. It's cheaper to store rules on a boundary and generate interiors than to track every interior pixel. Noether's theorem, symmetry implies conservation. We'll tighten this compression story next, but the moral's already clear. Key takeaway for you: if information costs, precision is a budget choice. The universe spends bits where they buy stability, function, and predictability, and compresses everything else. Now, if there's a cost to deciding and a cap to storing, what about speed? How fast can the universe even update? That's where the next constraint bites hard. The speed limit as a budget rule. See Margolus-Levitin. If bits have bills, there's a second constraint that hurts just as much: how fast you're allowed to spend. Everything clicked for me when I realized the speed of light isn't just a trivia fact about photons. It's a budget rule for causality. And quantum mechanics piles on with a separate cap. Even with energy in your pocket, there's a maximum rate at which a system can switch between distinguishable states. Throughput and latency, both capped. Okay, so basically, two constants govern the ledger. First, C sets the maximum reach of influence per unit time. No update can propagate faster. Second, the Margolus-Levitin bound sets the local clock rate. With average energy E above your ground state, you can do at most 2 EH distinct state flips per second. More energy, faster ticks. Less energy, slower ticks. No amount of cleverness turns 1 joule into infinite operations. Think of a simple micro example. 1 joule isn't much. You burn it walking a few stairs. The Margolus-Levitin number says that buys you on the order of 3 × 10^33 elementary operations per second. Huge, yes, but crucially finite. Now spread those operations over a large region you want to keep exquisitely up to date. The number of degrees of freedom balloons, your precise update budget plummets, and C prevents you from instantaneously coordinating distant parts. Result, you can't run the universe at infinite frame rate everywhere. You triage. Here's the weird part. We were taught C is about light, but it's deeper. C is baked into Maxwell's equations, sure, yet it's also the conversion factor that keeps cause before effect in every inertial frame. If you let influences outrun C, you create race conditions. 2 observers disagree about which event happened first. That's fatal to any consistent computation. The cap on propagation speed is nature's way of preventing contradictory writes to the ledger. Everything clicked harder when I paired C with Margolus-Levitin. Picture a giant distributed system. The energy you allocate locally sets your tick rate. The spacetime fabric sets your message delay. That's exactly how we build reliable simulations. Accept a finite communication horizon, avoid speculative cross-node guesses that create contradictions, and reconcile when signals arrive. Relativity feels like that. Slower but stable beats fast and inconsistent. Let's get concrete with numbers you can feel. Take a lab-sized region, say a cubic meter, filled with air at room temperature. There's a finite thermal energy sloshing around. So there's a ceiling to how quickly that cubic meter can evolve into mutually distinguishable microstates. If you insisted on tracking every molecule's position and momentum with absurd precision in real time, the ops bill explodes. Even with all that energy, most of your ticks would be spent just keeping up, not doing anything useful. The universe avoids that waste by compressing dynamics into conserved quantities and effective variables. More on that next. But the reason it must is this budget: finite ops and finite reach. Now what about entanglement? The place where people think quantum tricks might cheat see. Here, that's what most people miss. Entanglement creates strong correlations, yes, but without a classical message, you can't control what your partner sees. Signaling still requires a distinguishable change at the receiver, and that change must be delivered by something that travels no faster than c. In other words, entanglement gives you shared random bits. It doesn't give you superluminal bandwidth. The budget holds. Local energy sets your tick rate, c sets your delivery window. Micro story. I once helped debug a distributed simulation of a plasma. We tried a predictive push, so nodes would guess neighbors' next states to hide latency. It screamed until two guesses collided. Different parts of the grid believed different histories, and the run blew up. We fixed it by enforcing a finite light cone. No update finalized outside its causal neighborhood until messages arrived. Slower on paper, but now the simulation never contradicted itself. Relativity reads like that fix written into the fabric. Credibility check. The Margolus-Levitin bound comes from Anil Margolus and Lev Levitin's 1998 result. The minimum time to evolve to an orthogonal state is at least h/4e for time-independent Hamiltonians. Stated as a rate, that's 2 EH operations per second. Combine that with c from special relativity, Einstein's 1905 framework baked into Maxwell's equations and every relativistic field theory, and you've got a principled ceiling on local clock and global reach. These aren't speculative, they're standard results. Here's the practical implication for you. Every high-speed thing you care about negotiates with these caps. Cameras chase higher frame rates by pouring in energy and reducing noise, but they hit shot noise and heat. Fiber links push bits close to Shannon capacity, but signal shaping and repeaters still respect C. Quantum computers can do exotic parallelism in Hilbert space. Yet their logical gate rates are limited by control energy, coherence, and readout. Again, ops per joule and no faster than light fanout. The simple version: energy buys you clock, C limits your reach per tick. That turns speed of light from mysticism into middleware. And once your clock and reach are capped, brute forcing detail everywhere is impossible. The only winning move is to compress, store rules, conserve what you can, and update only what matters. That's why symmetry and conservation aren't just elegant, they're cheap. Compression everywhere, symmetry, conservation, Noether. Here's what most people miss. Once your clock rate and reach are capped, the cheapest move isn't to track everything, it's to shrink the description. And the master tool for shrinking is symmetry. Okay, so basically, a symmetry is a change you can make to a system that doesn't change the facts you care about. Rotate a perfect sphere, same sphere. Slide a crystal by one lattice spacing, same crystal. If the description doesn't change, you don't pay to store new data. You store the rule that generates copies. That's compression. Everything clicked for me when I connected that idea to Emmy Noether's 1918 theorem. She proved that every continuous symmetry of the action produces a conservation law. Time translation symmetry. Physics works the same today and tomorrow, yields energy conservation. Space translation symmetry. Same rules here and there, gives momentum conservation. Rotation symmetry. No preferred direction, gives angular momentum conservation. Those conserved quantities are like checksums. You don't track every microscopic shuffle. You keep a few invariants that constrain the entire evolution. Lossless compression for dynamics. Think of conservation as caching. If total energy can't change, you don't recompute that sum every tick. You carry one number forward and let it vet every interaction. Momentum conservation nails collision outcomes without simulating each atom in both objects. Angular momentum saves you from tracking the torque of a trillion tiny forces if the net is zero. You're not ignoring reality. You're reusing structure to avoid redundant bookkeeping. Micro story. I once tried to describe wallpaper to a friend tile by tile. She rolled her eyes. Give me one patch and the rule repeat. Exactly. The tear in the wallpaper. That's the real data. Physics works the same. Symmetry compresses the regularities so the deviations, the interesting parts pop. Here's the weird part. We treat elegant laws like an aesthetic win, but elegance is thrift in disguise. Maxwell's equations compress mountains of electromagnetic phenomena into 4 lines because of deep symmetries: Lorentz invariance and gauge invariance. The standard model looks busy, but compared to listing every scattering outcome, it's a tiny program generating huge behavior. General relativity does the same trick. Demand diffeomorphism invariance, no privileged coordinate labels, and geometry becomes dynamics with a minimal rulebook. Gauge symmetry is economy at work. Multiple mathematical descriptions correspond to the same physical state, so you only store equivalence classes, the invariant content, not the redundant gauge choices. Lorentz symmetry lets you compress all inertial perspectives into one invariant interval. You don't keep a separate universe for every velocity. Renormalization adds ruthless budget discipline. As you coarse grain, averaging over short distance wiggles, most couplings fade. Only a handful of relevant parameters survive to control large-scale behavior. Translation: ignore the expensive microdetail unless your resolution demands it. Okay, so how does this save compute under the caps we just set? Local rules plus conservation laws turn evolution into an ON algorithm. Each site talks to neighbors, updates with constraints, and passes on a few numbers that must hold. You don't broadcast global state every tick. And because C forbids instant coordination, these invariants act like low-cost messages that keep distant regions compatible without heavy synchronization. It's distributed consistency for almost free. Symmetry breaking looks like a failure until you do the accounting. When a magnet cools and picks a direction, it stores a bit, the chosen orientation. That local spin buys macro-level compression. The messy microscopic spins reduce to an order parameter and a few soft goldstone modes. You pay for the choice, then amortize the savings across the whole material. Nature spends bits where they create robust, compressible structure. Even chaos gets compressed statistically. You can't predict every swirl in a turbulent flow, but the distribution follows scaling laws. Thermodynamics is the ultimate compression engine. It reduces astronomical microstates to temperature, pressure, and a few relations because permutation symmetry over microconfigurations, plus conservation pins down the macrostates. That's deliberate lossiness tuned to your resolution. Let's get practical. Particle colliders aren't drowning in raw coordinates. They lean on symmetries to slash the search space. Use translational symmetry to define the center of mass frame, rotational symmetry to average over angles, and conservation to reconstruct invisible particles from missing momentum. The expensive computation, the brute force microstate tracking, never happens because the invariants steer you straight to the anomalies. Credibility markers. Noether's theorem 1918 is standard. Gauge symmetry and Lorentz invariance underpin Maxwell, quantum electrodynamics, and the Standard Model. Renormalization and the renormalization group, Wilson's 197's revolution, explain universality at critical points. None of this is fringe. It's the backbone of modern physics. Here's the counterintuitive payoff for you. You toss a ball, and your 20-watt brain predicts the arc because symmetry and conservation annihilate irrelevant detail. You look at the night sky, and cosmic isotropy compresses the view to a uniform backdrop with tiny deviations, the data-rich bits that teach us about the early universe. Your cognition rides on the same economy: store rules, flag surprises. So the pattern's clear. With a finite ops budget and a finite speed of influence, the universe can't update every pixel at infinite fidelity. It survives by compressing symmetry, caching conservation, and pushing detail to the margins. But compression alone isn't enough. You still need a policy for when to commit bits. That's where quantum measurement turns thrift into a render strategy. Reality renders at need, quantum measurement. If the universe can't afford to update every pixel every tick, it waits to commit until something forces its hand. That's the clean way to read quantum measurement without the fog. Okay, so basically, a quantum state is a compact to-do list of possibilities. It evolves reversibly and cheaply under Schrödinger's equation. No heat, no paid deletes. The bill shows up only when an interaction leaves a durable record that says, "This happened." That commit is where energy and entropy move. Think of the wave function as deferred computation. Amplitudes carry options. Phases carry how options will interfere. Until a record exists, the system keeps alternatives alive in superposition because it's cheaper than finalizing. The moment a measuring device couples and amplifies a microscopic difference into a macroscopic mark, an ionized trail, a voltage pulse, a pointer deflection, you've written a bit that would cost kT ln2 to erase at the device's temperature. That's Landauer walking into quantum mechanics, committing an outcome rights to memory. Erasing that memory has a minimum heat price. Here's what most people miss. The observer can be a warm table, a dust grain, or a camera. Mine not required. What matters is decoherence. The system gets entangled with many uncontrolled degrees of freedom, and the relative phases that enabled interference disperse into the environment. In practice, you can't gather them back. The environment selects a stable, pointer basis of states that resist further scrambling, exactly the ones that look classical to us. No neon, collapse in the equations, just unitary evolution making records irreversibly readable. Everything clicked for me with delayed choice experiments. In John Wheeler's setup, you decide at the last moment whether to close an interferometer. Keep it closed and you see fringes. No which path record exists, so the cheap superposition survives. Open it so which path information becomes available and the fringes vanish. Because a record is possible in principle, you must render a path-like outcome. The timing feels spooky, but the logic is tidy. The final pattern must be consistent with what could be known from the records you allowed. The universe isn't editing the past, it's enforcing bookkeeping. Quantum eraser sharpens the point. Tag paths with entanglement so interference disappears. Then erase the tags by measuring a partner photon in a recombined basis. Sort the original detections by those partner outcomes and interference reappears in the subensembles. No backward signals, no free messaging. What you're seeing is accounting, where which path info is accessible, the system paid to render a path. Where it's provably inaccessible, the superposition stays cheap and shows up as fringes. The rule is about records, not magic. Okay, so how do we connect this to budgets? Unitary evolution is lossless compression. It preserves information and costs no erasures. Measurements that leave stable marks are lossy commits. They cost thermodynamically and they prune alternatives. Nature defers those costs until interactions amplify enough to publish to the environment. That's why most microscopic processes cruise in coherence until they hit a detector or a chaotic bath. If you want to keep coherence, you must spend to isolate, cool, and error correct. Real money for real labs. Quantum Darwinism puts it into everyday language. The states we all agree on are precisely those redundantly recorded in many fragments of the environment. Your eyes read scattered photons off a chair. Mine read different photons. If both sets carry the same few bits, position, color, shape, we agree that the chair is there. Redundancy is cheaper than synchronizing full microstate logs. Publishing the same small set of outcomes broadly is an efficient way for many observers to share a world model. Microstory. A student once asked, "When does the electron decide?" I gave her 2 envelopes. One already contained a printed answer. The other contained a coin and instructions to flip it on camera. She opened the first, definite. She opened the second only when the camera rolled. The moment of the flip, a record was created. She nodded. So the decision is when it hits the world's memory. Close enough. The full math is entanglement and decoherence, but the economic intuition is right. Records are renders. Credibility markers, so you know this isn't hand-waving. Decoherence theory is standard, jerk, and others formalized pointer states and environment-induced superselection since the 198s. Wheeler's delayed choice is classic. Quantum eraser variants are replicated. Landauer's thermodynamic cost shows up in nanoscale experiments since the 200s, measuring work close to kT ln2 per bit. Quantum Darwinism has multiple experimental hints in photonic and solid-state systems, showing redundancy of classical information in environmental fragments. Here's the practical outcome for you. The solid world you experience is the subset of states that are cheap to keep and easy to copy. Positions, pointer readings, stable macroscopic facts. Fragile phase relations, what make quantum weird, are expensive to maintain against environmental assault, so you don't encounter them without careful lab work. Your reality is a cached render, optimized for agreement and stability, not a full-resolution log. The counterintuitive part is liberating. Superposition isn't mystery, it's lazy evaluation. Collapse isn't metaphysics, it's the price of writing. You can move the line between cheap evolution and paid commit by engineering the coupling, but you can't delete the bill. And that pushes us straight into the next survival trick. If you defer commits and the environment is noisy, how do you keep the important information alive? You don't protect it in one place, you spread it. That's error correction. Error correction in physics, topological phases, codes. Deferred commits are cheap, but coherence is fragile. Cheap systems drift. So nature does what good engineers do. It stabilizes the bits that matter by spreading them out so local noise can't easily kill them. That's error correction in plain language. Store information in patterns, not in parts. Okay, so basically, classical error correction repeats and checks. You might encode a single bit across 3 wires and majority vote if one flips. Quantum error correction has a catch. You can't copy an unknown quantum state. So you hide one logical qubit inside entanglement across many physical qubits, then measure only collective stabilizers, parity-like checks that reveal where errors happen without revealing the encoded state. The data is in any one qubit. It's in the correlations. That's resilience by design. Everything clicked for me when I learned the surface code. Lay qubits on a 2D grid. For every small square, measure 2 kinds of stabilizers, one that checks X-type flips and one that checks Z-type flips. Errors show up as little syndrome blips at the ends of strings. As long as those strings don't stretch across the entire lattice, you can infer and undo them by pairing blips along the most likely paths. Meanwhile, the logical qubit lives in a non-local loop that wraps around the grid. You'd have to cut a path all the way across to flip it, a move local noise almost never achieves by accident. Here's the weird part. That same data in the loop, not the link, logic shows up in real materials. Topological phases, like fractional quantum Hall states or topological superconductors, store information in global, non-local features that local pokes can't touch. Anyons in 2D systems have braiding statistics. Move one around another, and the joint state changes in a way that depends only on the topology of the path, not its details. To flip the stored information, you'd have to carry an enyon on a wind-around-the-world tour. Local jostles won't do it. That's a physical code, logical bits encoded in the fabric of the system's global order. Microstory. I once taught this with a rope and knot game. We looped a rope around the room to represent a logical qubit and sprinkled knots as local errors. People could slide knots, cancel pairs, and shout parity where ropes crossed. The big loop never changed unless someone cut the rope across the room. Everyone saw it. The message wasn't in any knot. It was in the loop. That's why topological order laughs at small perturbations. Now zoom out to geometry. In the AD-SCFT correspondence, the most studied holographic duality, everything in a higher dimensional bulk, spacetime is encoded in a lower dimensional boundary quantum theory. That sounds abstract, but here's the payoff. The mapping behaves like an error-correcting code. Work by Harlow, Almeri, Dong, Henningsen, and others, plus toy models like the HOPPY code, show that a single bulk operator can be reconstructed from many different overlapping boundary regions. Lose a chunk of boundary qubits and you can still recover the bulk, up to a threshold. That's exactly what good codes promise: redundancy and locality of checks, with the logical content delocalized. Think of the HOPPY code as a tiling of little encoders over a hyperbolic disk. Each tile spreads a few input degrees of freedom to more outputs, and the whole network makes the bulk-to-boundary map. If you erase some outputs, other overlapping regions still invert the map. The where of a bulk excitation is this pixel. It's this recoverable pattern across many boundary patches. Geometry, in this view, is the ledger of which patterns can be recovered from which subsets, error correction written in area and distance. Black hole physics adds credibility. The Ryu-Takayanagi formula equates the entanglement entropy of a boundary region to the area of a minimal surface in the bulk. Later, quantum extremal surfaces and the island formula solve the black hole page curve puzzle. As a whole evaporates, the entanglement wedge that reconstructs interior degrees of freedom can jump to include parts of the radiation. Translation: who owns the information is determined by an error correction-like rule that reassigns reconstructability as conditions change. The code protects unitarity while geometry adjusts to keep recoverability consistent. Here's what most people miss. Error correction isn't waste. It's the cheapest path to reliability at scale. You pay a fixed overhead to encode globally, then you run constant, local, cheap checks. You don't micromanage every degree of freedom. You stabilize the logical ones that carry meaning at your chosen resolution. In physics, curvature, entanglement structure, and horizons look like the stabilizers and checks that keep the macroscopic render consistent against the microscopic hiss. Credibility markers so you can track the receipts. Quantum error correction is standard, Shor, Steen, and the stabilizer formalism from the 199s. Surface codes by Kideve and later Fowler and colleagues. Topological order and Enians from Laughlin, Wen, and Nayak. ADAS-CFT is Maldacen in 1997. Holographic error correction pioneered by Almeri, Dong, Harlow circa 2015. HOPPY code from Pastowski and collaborators. The page curve resolved with islands by Almeri, Engelhardt, Marolf, and Maxfield in 2019-202. These aren't fringe claims, they're peer-reviewed milestones. Okay, so what does this buy you? Precision where it matters can be cheap if you place it in the right degrees of freedom. Quantum computers are learning this the hard way. Physical qubits are noisy, so we encode logical qubits and constantly measure stabilizers. Nature seems to do the same at grander scales. Spread the crucial information in non-local patterns, enforce local checks through dynamics and geometry, and let global order be robust by construction. The counterintuitive part is empowering. If the universe is optimized, it won't keep raw microdetail pristine. It will protect the few bits that anchor predictions, charges, topological indices, causal structure, behind redundancy. That's how a low-power brain, a noisy lab, and a jittery cosmos can still agree on chairs, stars, and the timing of a pulsar tick. So the thrift playbook now has 3 moves: defer commits, conserve with symmetry, and stabilize with codes. And when you put those together, you expect to hear the irreducible hiss that sets the floor, the noise you can shape but never delete. That noise is our next receipt. The unavoidable noise floor, Planck scales, quantum limits. If the universe runs on a budget, there has to be a resolution floor, a smallest blur you can't clean up by spending smarter. Okay, so basically, quantum mechanics and gravity team up to set this floor. Heisenberg gives you the trade-off. Sharpen one thing and you smear its partner. Gravity adds a surcharge when your measuring gear gets too energetic. Together they say, below a certain scale, the very act of trying to resolve more injects the noise you're fighting. Start with the cleanest invoice, the uncertainty principle. Deltax delta greater or equal to h//2. In plain terms, if you demand position accuracy deltax, you must tolerate momentum uncertainty delta of at least h//2 deltax. That added momentum means a spread in velocities. Wait a beat and your carefully localized packet blurs again. You don't pay once and keep crisp forever. Precision is a subscription, not a purchase. Push deltax smaller, the monthly bill rises. Here's the weird part. Even at absolute zero, no thermal jiggle, there's zero-point motion. Every harmonic mode carries a floor of energy, h/2. That vacuum isn't empty, it's fizzing with fluctuations. Try measuring an electromagnetic field with a perfect detector, and you still encounter half a photon of noise per mode. In optics, we call it shot noise and vacuum noise. The variance in counting photons follows Poisson statistics. Variance equals the mean. Double your light, and your signal-to-noise improves only by the square root. 10 times cleaner demands 100 times more photons, energy you may not have, or heat you can't dump. Everything clicked for me when I watched gravitational wave detectors wrestle with this. LIGO and Virgo squeeze light. They reduce uncertainty in the measurement quadrature at the expense of the conjugate quadrature. It's precision balloon. You borrow clarity from one variable and repay with extra noise in the other. There's no free lunch. There's an uncertainty budget you can rearrange but not shrink below h//2. The fact that these machines hit the quantum backaction wall is a loud signal. The floor is real. Now tie in gravity. To localize a particle within deltax, you typically need momentum on the order of h/deltax, which means energy. Pile in enough energy in a small region, and by general relativity, you curve spacetime. Push too far, and you create a mini black hole. That's the Bekenstein warning phrased operationally. Attempts to cram excessive information into a region backfire as horizons form. Combine h/c and g, and you get Planck length about 1.6 times 1035 m, and Planck time roughly 4 times 1044 s. We don't know that spacetime is literally pixelated at that scale, but we do know our current theories mutually shout stop signs there. Beyond it, your rulers and clocks become their own obstacles. Let's make the bandwidth trade-off tangible. Suppose you aim for a position resolution of 1020 meters, way beyond current tech. The required momentum spread is on the order of h/deltax, which is enormous. That momentum implies kinetic energy large enough to rattle the system, heat your apparatus, or add radiation pressure that kicks your mirror. Try to damp that, and you introduce thermal noise. Cool to near absolute zero, and quantum fluctuations still remain. Squeeze light to beat shot noise, and radiation pressure noise rises. You're sliding around a fixed product bound. You can shape the hiss, not erase it. Vacuum fluctuations aren't just theory curiosities, they leave receipts. The Lamb shift in hydrogen, the slight offset in energy levels measured in the late 194s, comes from vacuum polarization. The Casimir effect pulls two uncharged parallel mirrors together because the allowed vacuum modes between them differ from those outside. These effects are small but robust. If the vacuum were truly quiet, those shifts wouldn't exist. The ground state talks, softly but measurably. What about spacetime grain beyond these floors? Here, S where we draw a bright line between speculation and data. Some proposals predict tiny Lorentz-violating dispersion at extreme energies, high-energy gamma rays arriving slightly later than low-energy ones from the same burst. Fermi, MAGIC, and HESS have mostly found nulls, pushing any linear dispersion to scales at or above the Planck energy. Others predicted holographic noise, a correlated shear-like jitter in position measurements. Around 2009, GEO 600 reported unexplained noise near a frequency Craig-Hogan's model anticipated. After a readout change, the excess vanished. Hogan revised his calculation and built the holometer at Fermilab to target the updated prediction. Results so far: no confirmed detection. Caution wins. The simplest grain pictures are heavily constrained. Here's what most people miss. Noise floors aren't excuses, they're design specs. Metrology treats Heisenberg, shot noise, and back action as line items. Engineers fight them with quantum non-demolition tricks, measure variables commuting with the Hamiltonian so back action lands elsewhere, with squeezing, with cryogenics, with clever geometry. All of that is redistribution within an immutable budget. The floor is the friend that stops you wasting money on promises physics won't keep. Micro story. A colleague and I chased a stubborn bump in a spectrum for weeks, swapping fibers and detectors. The bump wouldn't die. It matched the predicted 0-point contribution. He grinned. That's the ground state saying hello. We logged it as a feature, not a bug, and redesigned our measurement to live with it. What this actually means is low-res isn't jagged pixels in the sky. It's a quiet, universal hiss that sets the minimum blur on every measurement. You'll hear it as shot noise in your best photodiodes, see it as vacuum-driven shifts in atomic lines, and feel it as back action when you try to pin a mirror's position too hard. Try to overpay for resolution, and gravity adds late fees. That floor isn't defeat, it's the map's edge. And right past that edge, gravity looks less like a force and more like the bookkeeper that keeps the budget balanced. Gravity as an emergent bookkeeper, entropic quantum gravity. When your measuring stick's energy starts curving the thing you're measuring, you've left metrology and entered accounting. That's the hint. Gravity might not be a fundamental push, but the ledger's response when information and energy move. Okay, so basically, if information capacity scales with area and committing bits has thermodynamic costs, then geometry can act like the balance sheet that keeps everything consistent. Shift energy, shift entanglement, and the shape of spacetime updates so causality, capacities, and costs still match. Here's what most people miss. Ordinary forces can be screened or canceled. Gravity just adds. That's what a constraint does. You don't cancel a budget by hiding receipts. You rebalance. Move mass energy and spacetime reassigns who can talk to whom and how quickly by bending geodesics. The force is the system's cheapest way to preserve consistent bookkeeping under finite bandwidth and storage. Now the receipts. First, horizons behave like thermodynamic objects. If you accelerate hard enough, the Unruh effect says you see a thermal bath with temperature proportional to your acceleration. Parked near a black hole horizon in Hawking's 1974 calculation says the hole radiates with temperature set by surface gravity. Temperature and entropy tied to area are not optional flourishes. They scream that horizons are where information accounting becomes macroscopic thermodynamics. That's a bookkeeping vibe, not a new field glued on top. Ted Jacobson gave this teeth in 1995. He assumed that for every local Rindler horizon, tiny patches seen by accelerated observers, the Clausius relation holds. Delta Q equals T delta S, with entropy proportional to area by the same 1/4 GH factor we saw. Demand that this thermodynamic identity is valid for all such patches, and out pop Einstein's field equations as an equation of state. In other words, gravity can be read as the continuum thermodynamics of an underlying information medium. That's not poetry, it's a derivation. Everything clicked harder with entanglement geometry. In many local quantum systems, the entanglement entropy of a region scales with the boundary area, not the volume. In holographic theories, best understood in de Sitter space, the Ryu-Takayanagi prescription equates the entanglement entropy of a boundary region to the area of a minimal bulk surface anchored on that region, divided by 4 GH. That's a dictionary. Change entanglement, change areas. Change areas, change geometry. If you treat entanglement as the wiring diagram, distances and curvatures are the cheapest index structure that reproduces which subsystems can reconstruct which others. Here's the weird part. This isn't just geometry wearing an information hat. The map behaves like an error-correcting code. In add-SCFT, a single bulk operator can be reconstructed from many overlapping boundary regions, redundancy plus locality, classic code behavior. As conditions change, the entanglement wedge that can recover bulk data shifts, like a file's permissions updating when you reshuffle parity blocks. Recently, the island formula extended this to evaporating black holes. The region whose entropy you count can include parts of the interior, and the page curve emerges. The ledger keeps unitarity by reassigning who owns the information, with minimal surfaces as the update rule. Microstory. Think of a network engineer staring at a congested map. Some links saturate, queues build, routes reflow. You don't add a new force. You recompute shortest paths given current loads. In gravity, mass energy and entanglement set the loads, and geodesics are the recomputed cheapest routes for causal influence. Curvature is the routing table adjusting so packets, fields, signals, influences propagate without contradiction and within capacity. Eric Verland pushed a bold entropic take in 201. Gravity can emerge as an entropic force from statistical tendencies of microscopic degrees of freedom on holographic screens. Move a mass closer to a screen. The number of accessible microstates changes. With a temperature set by horizon physics, you get an effective force that recovers Newton's law in the right limits. Whether every detail survives observational tests is still in play, but the through line fits our budget story. Gradients in information count, and temperature produce motions that look like forces, because that's the cheapest way to increase entropy. Okay, caveat time. Add SCFT is clean in negatively curved spacetimes. Our universe is not AD-S. equals EPER. The slogan tying entanglement to wormhole-like connectivity is a provocative conjecture, not a theorem. And entropic gravity faces constraints from galaxy rotation curves and lensing. But the non-negotiables are strong. Horizon thermodynamics with area law entropy, Jacobson's thermodynamic route to Einstein's equations, area law entanglement in quantum field theory, and holographic relations where entanglement maps to areas. Across these, geometry reads like the cheapest consistent index for information flow. Here's what this actually means for you. Gravity isn't a mysterious extra ingredient. It's the operating system's memory manager. Put energy here, and the manager allocates capacity and updates pathways so signals stay causal and storage quotas, area-based, aren't violated. Try to overpack bits in a region, and the manager throws up a horizon, a boundary ledger that caps capacity and meters I/O as Hawking flux. Move stuff around and freefall looks like no force, locally because the best bookkeeping keeps local frames simple, pushing the cost to curvature gradients you only feel when you compare frames. The counterintuitive payoff is that spacetime might be a byproduct of optimizing under constraints, not the stage itself. If connectivity is entanglement and capacity is area, then the shapes we draw are reflections of deeper information structure arranged to keep compute cheap and consistent. That's the same thrift we've seen all along, now written as geometry. Black holes as the budget's edge cases. If spacetime is the operating system's memory manager, black holes are the places where the budget hits the hard limit and the OS switches into emergency mode. Okay, so basically, a black hole forms when you cram so much energy, and therefore potential information, into a region that the cheapest consistent move is to seal it off with a horizon and move the bookkeeping to the boundary. Start with the loud receipt, the Bekenstein-Hawking area law. The entropy S of a black hole equals its horizon area divided by 4gh stroke, with KB set to 1. That's brutal and precise. Maximum bit count scales with area, not volume. Translation: the interior isn't a giant warehouse of individually tracked microstates. The system writes its archive on the surface in Planck-sized pixels. It's the ultimate compression, surface-only storage when bulk tracking would blow the budget. Now add Hawking's 1974 result. Quantum fields near the horizon don't divide neatly into inside and outside. Pairs fluctuate. One mode escapes with a thermal spectrum, the other falls in. To distant observers, the hole radiates like a blackbody at a temperature set by its surface gravity. Big holes are cold and evaporate slowly. Small holes are hot and evaporate quickly. The same geometry that sets the storage quota also sets the leak rate. That's elegant accounting. Capacity and garbage collection tied to the same area. Here, S where everyone once panicked, the information paradox. If the radiation is perfectly thermal, then as the hole evaporates, information disappears, violating quantum unitarity. But Don Page analyzed what should happen if the global evolution is unitary. The entropy of the radiation rises at first as the hole scrambles and emits, peaks at the Page time, then falls as late-time radiation becomes correlated with the early emissions. That Page curve is the signature of a good code at work. You scramble, distribute, and eventually release the message, not as clean packets but as long-range correlations. Everything clicked when we learned how to compute that curve from the gravity side. The island formula, developed around 2019-202 by Almeri, Engelhardt, Marolf, and Maxfield, adds quantum extremal surfaces to the entanglement calculation. As evaporation proceeds, the extremal surface can jump so that the radiation's entanglement wedge includes part of the interior. Operationally, the reconstruction rights shift. What looked like inside the hole becomes encoded in the radiation outside. That's error correction logic. The logical degrees of freedom move between subsystems, while redundancy keeps the ledger consistent. Microstory. A friend once asked, "Is a black hole just a hard drive you can't open?" I said, "Closer to a write-only archive that slowly mails you scrambled postcards. If you collect every postcard in order and you know the code, you can reconstruct the file." She groaned, fair, but got it. Unitarity doesn't promise convenience. It promises that information isn't truly lost, only deeply encoded and painfully slow to retrieve. Scrambling matters here. Hayden and Preskill argued that black holes are fast scramblers. Toss in a diary after the Page time, and it becomes reconstructible from the outgoing radiation after only a scrambling time plus a modest delay. That's the behavior of a high-performance mixer. It hides information quickly inside while still allowing, in principle, recovery from a relatively small fraction of outputs. From a budget view, that's ideal. Rapid, robust encoding that protects content against local noise. Here's the weird part. From far away, black holes are bald. Mass, charge, spin, no hair. That's aggressive compression. Throw in a violin or a textbook. The external fields barely change beyond those three numbers. The fine-grained details sink into microscopic horizon degrees of freedom that don't advertise themselves. Only through the long, correlated Hawking stream can any of that specificity leak back out. Minimal public metadata, maximal internal redundancy. What about the firewall debate? Late radiation must be entangled with early radiation to return information, but near-horizon smoothness seems to require entanglement across the horizon. Monogamy says you can't have both maximal at once. One resolution is that the interior modes are not independent. They're encoded non-locally in the radiation. equals EPR, the conjecture that entanglement corresponds to wormhole-like connectivity, is a suggestive way to say that inside geometry can emerge from correlations outside. Whether or not literal wormholes are involved, the budget-friendly move is clear. Keep quantum mechanics intact and let the code's notion of where flex. Cosmic censorship fits the accounting story too. Singularities, places where the effective description breaks, are hidden behind horizons. That's a privacy policy from the OS. Undefined behavior is sandboxed so external evolution remains well posed. You can compute the outside world without referencing unphysical internals. Credibility markers so you know we're on firm ground. Bekenstein's 1973 bound, Hawking radiation in 1974, Page's analysis in the 199s, fast scrambling from Sekino and Susskind, Ryu Takanagi and quantum extremal surfaces linking entanglement to area, Island formula reproducing the page curve in solvable models. These are mainstream results and active frontiers, not fringe speculations. Here's the practical implication for you. Black holes are the budget's edge case handlers. They set hard limits on storage density, bits per area. They meter I/O via temperature and evaporation. They enforce data integrity with horizons and scrambling. And they hint strongly that our universe runs on a code that prefers boundary bookkeeping, redundancy, and delayed, correlation-rich outputs over raw, interior micrologging. In other words, when the system maxes out, it chooses the cheapest consistent rule, and that rule writes on the surface. The cosmic background as a thermal receipt, CMB, neutrinos. If the early universe spent big, there should be a receipt. That receipt is the cosmic microwave background, the CMB, a faint glow filling the sky at about 2.725 Kelvin with a spectrum so perfectly thermal it stunned everyone. It's boringly uniform to 1 part in 100,000, yet those tiny ripples are packed with information. From a budget view, it's the invoice. Minimal inputs, maximal imprint. Okay, so basically, before about 380,000 years after the Big Bang, the universe was a hot plasma of photons, electrons, and protons. Photons bounced constantly off electrons, so light couldn't travel far. Pressure from radiation and gravity from matter set up acoustic waves, literal sound in the plasma. When things cooled enough for electrons and protons to combine into neutral atoms, photons decoupled and streamed freely. That last scattering snapshot is the CMB. The pattern of hot and cold spots is a fossil of those sound waves. Everything clicked for me when I saw how few knobs dial that sky. The angular power spectrum, those peaks and troughs versus multipole moment, isn't art, it's physics. The first peak marks the scale of the sound horizon, how far waves could travel before decoupling. Its position and height depend on the expansion rate and geometry. The relative heights of odd and even peaks reveal the baryon density. Baryons add inertia, boosting compressions over rarefactions. Cold dark matter shifts peak locations by sculpting gravitational wells. The overall damping tail at small scales, silk damping, is photon diffusion washing out fine features. That tail is a built-in low-pass filter. The plasma enforces a bandwidth limit, and the sky remembers it. Here's the weird part. A half-dozen parameters generate millions of data points. Planck's 2013 and 2018 releases fit the spectrum with a compact model. Baryon density, dark matter density, dark energy fraction, Hubble parameter, optical depth, and the primordial fluctuation amplitude and tilt. Tweak those and you match the whole sky. That's compression running at cosmic scale, a tiny header file rendered once everywhere. Inflation enters as the cheap randomness generator. A nearly constant energy density in the first sliver of a second drives rapid expansion, stretching quantum fluctuations to astronomical sizes. The output looks almost scale invariant, equal power per logarithmic interval, with a slight red tilt, just what the data shows. Whether every detail of inflation is right is still under test, but the thrift logic matches. Simple mechanism, broad correlations, few parameters. Let's talk neutrinos, the second line on the receipt. Neutrinos decoupled around 1 second after the Big Bang because they interact so weakly. You can't photograph the cosmic neutrino background directly, but you can see its fingerprints. Free-streaming relativistic species change the expansion rate and shift the phase of the acoustic peaks. Measure that subtle phase shift and damping, and you estimate NEF, the effective number of light species. The standard model predicts about 3.046. Planck and other data land right on it within errors. That's a clean itemized charge, 3 light relics paid in full. Micro story. A colleague once called the CMB the universe's QR code. Scan the peaks and your decoder spits out omega lambda h as ns. She was only half joking, that's what the likelihood pipelines do. The astonishing part is not that we can fit the data, it's that the best fit model is this small. In a world with finite energy and strict bandwidth, You want a renderer that writes rules, not pixels. The CMB is that render. Here, what most people miss. The near-perfect blackbody spectrum isn't a coincidence. Any significant energy injection after decoupling would distort it from a Planck curve. COBE-FIRAS in the 199s measured deviations at the parts per 10000 level and found none. Another receipt. No big late-time hacks. Tiny mu and y distortions are now targets for future missions, acting as auditors for small transactions like dissipation of small-scale power. Again, thrift means the big spend happened early and cleanly, then the ledger coasted. Baryon asymmetry is another budget clue. There's a slight excess of matter over antimatter, about 1 part in a billion. If it were 0, almost everything would annihilate, leaving photons and neutrinos only. That tiny imbalance seeds all later structure. It's an absurdly cheap knob with enormous downstream payoff, a recurring theme in optimized systems. Practical payoff for you. The CMB tells us we don't need infinite detail initial conditions. The universe wrote a tiny seed spectrum and a few densities, then let cheap, local fluid dynamics and gravity render the sky. That's the same strategy you use when you compress a video with a good codec. Predict frames from a model, store residuals, and let the decoder reconstruct. The CMB is the universe's compressed header. Neutrinos are the watermark that proves the encoding method. Credibility markers so you know the receipts are real. COBE discovered the blackbody spectrum and first anisotropies. WMAP mapped the peaks. Planck nailed the spectrum with high resolution. The neutrino phase shift has been measured statistically in the CMB. These are mainstream results with redundant checks across experiments. The bottom line is simple. The early universe didn't spray detail. It set rules and a few numbers, then let physics do the heavy lifting once. That's thrift at cosmic scale. Minimal description, maximal consequence, perfect for a system with finite energy and hard floors. Constants as hard caps, find structure alpha CH. Here, what most people miss. The constants of nature aren't decorative labels. They're the universe's hard caps, the dials that fix how finely, how fast, and how densely reality can afford to compute. Treat them like budget controls and the numbers stop feeling mystical and start feeling necessary. 4. Dominate your everyday world. The fine structure constant alpha, Planck's constant h or h-stroke, the speed of light c, and Newton's g each caps a different part of the ledger: bitrate, action granularity, causal bandwidth, and storage per area. Start with alpha, the fine structure constant. It's dimensionless, about 1/137, and sets the strength of the electromagnetic interaction. Okay, so basically, alpha is the bitrate for how charged matter exchanges information with the electromagnetic field. Raise alpha and electrons bind too tightly, spectra shift, chemistry locks up, and stellar nucleosynthesis goes sideways. Lower alpha and atoms barely hold together, molecules get flaky, and complex chemistry thins out. The cheap universe reading is simple. Alpha sits in a narrow window where M interactions are strong enough to build hierarchical structure, but not so strong that they overconstrain it. You want flexible building blocks under a cost ceiling. Alpha is that ceiling. Everything clicked when I framed alpha as the price per M interaction. The lower the price, the more freely information can flow through light and charges. But make it too cheap and you lose selectivity. Make it too expensive and nothing assembles. Precision spectroscopy, atomic clocks, and quantum electrodynamics all use alpha as the central input, and across cosmic time we've tested its stability. Claims of tiny spatial variations have popped up, but the most precise lab and astrophysical bounds say alpha hasn't budged beyond extremely small limits. Translation: the bitrate hasn't changed within our measurement reach. Stable budget, stable rendering. Now Planck's constant h, with h-stroke equals h/2 pi. H sets the quantum of action, the fundamental pixel size in phase space. Heisenberg's uncertainty products, deltax delta and delta delta, are pegged to h-stroke, which means h-stroke fixes the smallest effort per computation step in the physical world. If h-stroke were smaller, quantum fuzz would shrink. Classical behavior would dominate more easily. Zero-point energy would drop in ways that destabilize the nice thermodynamic accounting you rely on. If h-stroke were larger, coherence would be easier to maintain, but noise would balloon and macroscopic definiteness would be harder to stabilize. The cheap reading. H-stroke is the coin size in which nature pays for dynamical updates. You can't buy action in smaller denominations. Okay, so where does C fit? We already met it as the causal speed limit, the maximum reach per tick. But C is also the unit converter that unifies energy, mass, and fields. E equals mc2, and the same Maxwell's equations that gave us light tie C to electric and magnetic responses of the vacuum. In a budget sense, C caps propagation bandwidth. If you crank C up, causal cones widen and coordination gets cheaper. But you also change the balance of energies across every interaction, potentially wrecking atomic structure and stellar lifetimes. Turn C down, and the universe slows. Stars struggle. Horizons form more readily for the same energy densities, and communication is throttled. The point isn't to fantasize alternative worlds. It's to see C as the fixed slope between time ticks and spatial reach, the constant that keeps causal bookkeeping unambiguous. Then G, Newton's gravitational constant, which sets how energy curves geometry. People say gravity is weak, but that's a misread. Gravity is unscreened and cumulative. G determines how much curvature a given energy density buys. Shrink G and spacetime stiffens. Black hole thresholds rise. The Bekenstein bound loosens. More bits per area until other sectors crack. Grow G and spacetime softens. Horizons form easily. Storage capacity per region plummets. Complexity gets strangled by early collapse. Crucially, G appears in the entropy area law. S equals a /4gh stroke. That ratio is a storage quota written in geometric units. Lower h stroke or higher G shrinks the quota. Push the other way and you inflate it. Either way, the constants couple caps across thermodynamics and geometry. Here's the counterintuitive part. These constants don't act alone, they braid. Alpha depends on E2/4 pi, a combination that explicitly ties the M price to h stroke and C the Bekenstein, Hawking entropy scales as area divided by GH stroke, mixing gravity's storage rate with quantum granularity. Even the Margolus-Levitin bound, ops per second 2 EH plugs h stroke directly into the clock rate. In other words, the ledger's limits are cross-wired. Change one dial and the whole budget reprices. Credibility markers so you know we're not winging it. Alpha approximately 1137 shows up in atomic spectra and QED. Modern measurements pin it to parts per billion accuracy. H-stroke sits at the heart of quantum mechanics and every uncertainty relation. Metrology defines it via the Kibble balance linking kilograms to Planck's constant. C is fixed by definition in SI units and emerges from Maxwell's equations and relativity. G is measured by torsion balances and astrophysical fits. It anchors general relativity and black hole thermodynamics. What this actually means for you is clean. Alpha caps M bitrate, H stroke caps resolution per action, C caps causal throughput, G caps storage by area. Those caps show up in everything you touch. The color of the sun, the chemical table you cook with, the bandwidth of fiber links, the noise floor of your cameras, the stability of GPS, the shape of galaxies, the temperature of black holes. They set the menu, not just the prices. Micro story. I once sketched a control panel for a friend, 4 sliders labeled alpha H stroke C G, and asked her to nudge alpha up 5%. We walked the consequences. Spectroscopy drift, molecular bonds tightening, stellar fusion pathways shifting, carbon yields changing. She asked, "So life breaks?" I said, "Life as we know it gets priced out. Some other economy might emerge, but not ours." She didn't love that answer, but she saw the point. Constants define the viable market for complexity. The cheap universe thesis meets its mirror here. The values we measure look like the narrow regime where compute is possible, storage is sufficient, and causal coordination is reliable, without blowing the budget into triviality or collapse. We don't know why they take these values, selection, deep math, or dynamics, but we do know what they do. They enforce hard caps. And once you accept that, hunting for renderer artifacts becomes a targeted game, not a fishing trip. Hunting for artifacts tests for low-res reality. If reality runs on a budget, it should leave fingerprints, subtle, coordinated ceilings where different experiments start to saturate at the same scale. Not glitches, not UFOs, patterns that match a pre-registered shape. Okay, so basically, we're looking for cheapness under stress, places where the constants force a ceiling and the ledger's rules pinch hard enough to be seen. Here, that's what most people miss. A single anomaly can mislead. A family of linked limits that move together is powerful. The cheap universe thesis predicts that as you push timing, dispersion, and position sensitivity toward Planck-adjacent regimes, you'll see floors that tighten in sync when mapped through the same constants. If gamma-ray dispersion is bounded more strictly, correlated interferometer noise should tighten by a predictable ratio, and any pulsar timing wander with the same origin should drop in lockstep. That's the tell. Hunting ground 1, energy-dependent dispersion. If spacetime is an optimized medium, its symmetries might be exact at low energies but only approximate near a cutoff. That could show up as high-energy photons from the same gamma-ray burst arriving fractionally later than low-energy ones, after you subtract source effects. This is where Fermi, MAGIC, HESS, and soon CTA live. The sober news. Most linear in energy dispersion is already pushed to scales around or beyond the Planck energy by null results. Good. That's a constraint, not a failure. The move now is stacked analyses, many bursts, common pipelines, tight source modeling, to bound or reveal tiny quadratic terms. Shape first, claim later. Hunting ground 2, correlated interferometer noise, holographic like shear. The idea isn't that space shakes randomly. It's that positions might be defined only to a transverse accuracy that scales with area, producing a faint, direction-dependent jitter shared by nearby instruments. Around 2009, GEO 600 saw unexplained noise near a frequency Craig Hogan's holographic model anticipated. After switching to a new readout method, the excess vanished. Hogan revised the math, moving the predicted band, and built the Fermilab holometer to test it. Results so far: no confirmed signal. The right next step is a deliberately over-instrumented triangle, 3-kilometer scale, co-rotating interferometers with environmental channels blanketing seismic, thermal, and electronic paths, looking for a shear-like spectrum that co-rotates with the stars, not the building. Hunting ground 3, pulsar timing arrays, the universe's metronomes. Millisecond pulsars keep time to hundreds of nanoseconds over decades. PTA's already found a nanohertz gravitational wave background with a specific angular correlation, the Helling's Downs curve. A budget floor would show a different sky pattern and spectral slope, subtle, same sign wander across baselines that doesn't match gravitational waves or clock noise. The test is simple to state and hard to fake. Add a budget floor template to the joint PTA analysis, lock it before looking, and see if the sky prefers it. Cross-check with independent optical lattice clocks so your reference doesn't become the limit. Hunting ground 4, ultra-high energy anisotropies. A naive lattice leaves cubic fingerprints, tiny direction-dependent splittings at extreme momenta. We don't see Minecraft space. Limits are tight, but second-order anisotropies could still hide. Coordinate atomic spectroscopy of high-L states, spin precession experiments, and ultra-high-energy cosmic ray data in one sky-referenced frame across seasons. If a tiny preferred direction exists, a stack of diverse experiments should point to the same axis within errors. If they don't, you tighten the noose on cheap discretization schemes. Okay, let's operationalize this so it's not just vibes. A falsifiable bet looks like this. Pre-register 3 coupled observables tied by constants. A dispersion parameter eta and photon arrival time scaling as E/Fn. A correlated interferometer strain floor SHF, with a predicted shear spectrum and sky rotation, and a PTA angular correlation template B, theta, with a fixed spectral index. Define a mapping between eta, SH, and the amplitude of B via H stroke, C, and a single new effective scale lambda that parameterizes the low-res cutoff. Run all 3 analyses blind. If one tightens lambda, the other 2 must tighten by the mapped factors. If one loosens, the others should loosen. A mismatch kills the model. Micro story. A colleague once chased a gorgeous 1F bump exactly where a model predicted a floor. Champagne on ice. 2 weeks later, ground loop from a cryocooler. The bump vanished with a cable reroute. He laughed, then wrote the ground loop veto into every future run. That's the culture you want here. Predict shapes, angles, and cross-lab covariances so an instrument has to collude across continents to fake you out. Credibility markers so you know this isn't cherry-picking. Fermi-Lat and magic bounds on Lorentz violating dispersion are public and tough. HESS and CTA sharpen them. GEO 600's excess and its disappearance after a readout change are documented. The holometer nulls are on record. Nanograv, EPTA, PPTA, and IPTA have demonstrated sky-correlated signals and can test new templates. Spin precession and atomic clock Lorentz test sit under the SME framework with world-leading limits. The infrastructure exists. The trick is coupling the analyses with a shared parameterization and pre-registered expectations. Here's the emotional payoff. We don't need to catch the simulation rendering a pixel. We need one disciplined, shape-matched anomaly, or a family of coordinated nulls that together press the cutoff past where naive grain could hide. Either outcome is a win. A matched signal forces a rewrite. Coordinated nulls make the cheap universe claim earn a subtler story, thrift without crude discreteness. So why should you care? Because this is where big ideas grow up. The cheapness thesis isn't a slogan, it's a set of risks we can take in public. If we're right, the universe is running a brilliant optimization, and the floors will hum the same tune across wildly different instruments. If we're wrong, the tune will refuse to harmonize, and will have built the cleanest constraints in the process. Either way, reality pays the bill. The universe's thrift strategies, local rules, global payoffs. Here's what most people miss. Thrift isn't a patch on top of physics, it's the operating system. Once you accept finite ops per joule and a hard speed limit C, the only scalable strategy is to push cost to the edges, run cheap local rules, and let global structure emerge as a byproduct. The payoff is outrageous. Simple constraints, stunning universality. Okay, so basically, locality is your first savings account. Fields interact at the same point. Particles only nudge neighbors. That slashes compute from consider every pair to consider adjacent pairs. In complexity language, you go from ON2 to ON work per tick. Add causality and you get natural sharding. Regions beyond each other's light cones can update independently for many ticks without coordination. That's free parallelism handed to you by the geometry of spacetime. Everything clicked for me when I realized renormalization is the accountant that reconciles these choices across scales. You coarse-grain average over short-distance wiggles and watch parameters flow. Most couplings fade away as you zoom out. Only a tiny, relevant set survives, controlling large-scale behavior. Translation. Your simulator only carries the few knobs that matter at your chosen resolution and throws the rest into a cheap background. That's ruthless cost-cutting, backed by Wilson's 197's renormalization group. Effective field theory formalizes the discipline. You don't need a theory of everything to predict tomorrow's lab result. You write the most general local Lagrangian consistent with your trusted symmetries, then organize terms by dimension. Lower dimension operators dominate. Higher ones are suppressed by powers of a large cutoff scale lambda. In plain English, You can safely ignore exotic corrections until you pay the energy to make them visible. Just-in-time precision, instead of pre-computing the universe. Here's the weird part. Ignoring detail makes predictions stronger. Universality says wildly different microscopic systems hit the same macroscopic exponents at critical points because symmetry and dimensionality, not atom-by-atom detail, set the class. The Ising model, liquid-gas transitions, certain neural nets, same playbook. One cheap template explains a zoo. That's memory saved and discovery multiplied. Microstory. I once modeled a nasty fluid instability. Full Navier-Stokes at high resolution was brutal. We switched to an effective model, a handful of modes and 2 nonlinear couplings. Suddenly the essentials popped: eddies, energy cascade, saturation time, without simulating every microvortex. The client got decisions faster. We spent a fraction of the compute. That's the universe's vibe. Invest in the few variables that carry the story at this scale, let the rest average out. Okay, so how do locality and causality concretely save compute under the caps we've seen? Picture a lattice update. Each site queries neighbors, applies a rule, writes a new state. No global broadcast. Conserved quantities, energy, momentum, charge, act like checksums that propagate cheaply, constraining outcomes without heavy messaging. Because C forbids instant coordination, these invariants keep distant regions compatible with minimal chatter. It's distributed consistency for almost free. Renormalization plays middleware between layers. Quarks and gluons renormalize into hadrons at low energies. Hadrons renormalize into nuclei, nuclei into fluids, fluids into elastic continua. Each layer inherits constraints, symmetry, conservation, but pays only for a few scale-appropriate parameters: viscosities, sound speeds, elastic moduli. You never compute quark exchanges to predict a cello's tone. Elasticity covers it because that's the cheapest model consistent with the caps. Phase transitions showcase thrift and drama together. Near criticality, correlation lengths blow up, so small local rules generate long-range structure cheaply. After symmetry breaks, new effective fields, order parameters, goldstone modes, take over. You spend one global bit to choose a branch, then amortize that choice across the system with simpler variables. Nature pays once, then cashes dividends for miles. Even turbulence, everyone's favorite headache, obeys scaling laws. Kolmogorov's picture says energy cascades from large eddies to small with a predictable spectrum. You can't forecast every swirl, but you can compress the distribution with a few exponents and fluxes. That's the thrift theme again. Don't memorize the movie. Learn the genre and its parameters. Here's what most people miss about emergence. It isn't hand-waving, it's the cost model. Locality prevents non-local error blowups. Causality grants parallelism without contradictions. Renormalization kills microscopic dependence, making your predictions robust to small unknowns. That combination turns physics into a scalable algorithm. Cheap steps, bounded communication, stable summaries. Practical payoff for you. This is why engineering works. You design bridges with continuum mechanics, not quantum chromodynamics. You fly spacecraft with Newton and Einstein, not the standard model. You only buy microdetail when the scale demands it: semiconductors, superconductors, precision spectroscopy. Everywhere else, you ride the effective theory because it's the lowest bid that clears your accuracy target. Microstory. A robotics team I worked with tried to model motor noise down to coil windings. The controller lagged and jittered. We stepped back, wrote a coarse stochastic model with 3 parameters: bias, variance, correlation time, and fed that into a robust controller. Performance improved overnight. The moral was simple: the right coarse grain beats the wrong microscope. The counterintuitive payoff is emotional. Thrift doesn't cheapen wonder, it multiplies it. The fact that a small lawbook, symmetries, locality, conservation, and a handful of running couplings renders stars, storms, and synapses under brutal resource caps should make your jaw drop. This is 20 watts producing a conscious narrative, a few constants orchestrating a cosmic web. Constraint didn't crush complexity. It shaped it into something legible, reliable, and explorable. What this actually means is your best questions change. Stop asking for infinite detail where the budget won't pay. Start asking which effective variables carry the prediction at your resolution, which symmetries you can trust, and where a small spend, cooling, isolation, extra bits of redundancy, buys an outsized gain. That's how the universe runs itself. That's how you should run your models. Your reality, compressed, perception, computation, meaning. Here's the twist that hits home. Your brain runs the same thrift playbook as the cosmos. 20 watts, 2 fists of jelly, and yet it steers a body, plans a week, and imagines futures. It does that by compressing, predicting, and spending attention like money. Okay, so basically, perception isn't a camera, it's a codec. Your brain predicts what's about to hit your senses, compares that cheap forecast to incoming signals, and only pays for the error. That's predictive coding. Top-down models propose a scene, bottom-up data flags the mismatches. When prediction and input agree, the system coasts. When they don't, surprise spikes, circuits wake up, and you adjust the model. Think of attention as your GPU scheduler. You don't render the world at full resolution. You render a tiny foveal window in crisp detail and the periphery in broad strokes. Saccades, those rapid eye jumps, let you scan, stitch, and pretend the scene is stable. The brain bets pixels where expected value is highest. Threat, reward, novelty, goals. That's energy management, not metaphysics. Here's what most people miss. Illusions aren't bugs, they're the receipts for efficient priors. The checker shadow trick. Your visual system assumes uniform illumination and discounts shadows to keep surfaces stable across lighting. The Mueller-Lyer arrows. Your system interprets corners in 3D, not lines on paper. The Canessa triangle. Your brain prefers continuous objects, so it hallucinates edges to compress the scene. Those mistakes are the flip side of everyday speed. Everything clicked for me when memory slid into the same frame. You don't store experiences verbatim. You store compressed gist, schemas, and a handful of pointers to vivid details. Later, you reconstruct. That's why recollections feel crisp but drift with context. The brain trades exactness for utility. Faster retrieval, lower metabolic cost, better generalization. It's lossy on purpose, just like an efficient file format. Micro story. You know the invisible gorilla experiment. 2 teams pass basketballs, you count white shirt passes. A person in a gorilla suit strolls through, beats their chest. Half of people never see it. My friend didn't. She insisted the video was edited until replay. Then she groaned. That wasn't stupidity, it was a codec working under a budget. The task hijacked attention, the system suppressed irrelevant pixels. Okay, so where's emotion in this? It's bandwidth control. Dopamine and noradrenaline aren't just mood paint, they're the sliders for sampling and plasticity. Surprise plus relevance opens the spigot, more data, deeper processing, stronger updates. Boredom closes it. Anxiety diverts cycles to threat models, starving exploration. In a capped power brain, feelings are scheduling signals. Here's the weird part. Your feeling of a stable, richly detailed world is a hallucination that's good enough. Head turns, blinks, saccades. Your brain fills the gaps with model-based inferences and a sprinkle of fresh pixels. When fills match the world, you feel present. When they don't, you feel surprise, confusion, or awe. Presence tracks prediction error more than raw input rate. Language rides the same rails. It's the ultimate lossy codec, discrete symbols that other brains decompress using shared priors. Miscommunication isn't mysterious, it's a dictionary mismatch. Jokes and metaphors hack priors to produce high-value errors, those quick, aha bursts that justify attention costs. Stories are compression engines. They chunk messy events into causal templates so the model runs cheap and fast. So what do you do with this? 3 practical moves. First, invest in better models when the stakes are low. Varied inputs, slower attention, spaced repetition. Train the compressor. Later you'll decode richer scenes for the same cost. Second, offload state when stakes are high. Checklists, external memory, structured environments. Don't waste metabolic budget juggling details the world can hold for you. Third, treat error as data, not injury. The sting of being wrong is the learning signal that updates priors quickly. Micro story. I tried learning bird songs. At first the forest was white noise. Then I learned a few motifs: tea kettle, teacher, teacher. Suddenly the canopy wasn't noise, it was compressed messages I could parse while walking. 1 hour of model building bought months of richer perception at no extra power. That's the dividend of a good codec. Here's what most people miss about meaning. Predictive brains worship prediction error. We call near zero error understanding. We call manageable, interesting error curiosity. We call unmanageable error threat or mystery, depending on arousal. Purpose is a long game of placing yourself where the errors you chase are worth the energy, where learning returns more clarity than it costs. Now stitch this back to the cosmos. Earlier we saw how physics defers commits, compresses with symmetries, stabilizes with codes, and accepts noise floors. Your cognition mirrors that strategy. Defer rendering with predictions, compress with priors, stabilize with habits and culture, and budget attention against a hiss you can shape but not silence. You're a tiny, biological renderer negotiating with limits the universe set. The counterintuitive payoff is hopeful. Living in a cheap universe doesn't cheapen experience, it concentrates it. Constraints force creativity, efficient codes, shared stories, reliable tools. The better your models align with the environment's regularities, the richer your world feels for the same 20 watts. And when models break, that sharp jolt is your invitation to spend wisely. Look closer, update, and earn a clearer render. What this actually means is simple. You inhabit model space. The world you feel is the output of a budgeted decoder. Choose where to spend attention, train compressors that pay dividends, build environments that surface high-value surprises instead of junk noise. It's the same thrift we see in physics, expressed in thought. The one test that hurts, a falsifiable bet. Here's the brave bet. Pre-register one shared cutoff scale lambda, then demand 3 independent hits, tiny energy-dependent delays in gamma-ray bursts, a sky-locked shear spectrum in co-rotating interferometers, and a distinct non-Hellings, Downs angular pattern in pulsar timing arrays. Map all 3 amplitudes to lambda using H-stroke and C-run blind. If one tightens, the others must tighten by the mapped ratio. If one fails, the trio breaks. Pass or fail, we learn. That's science with skin in the game. The cultural cover-up, why we ignore cheapness. If the physics keeps whispering thrift, why do we keep hearing grandeur? Here's what most people miss. We don't ignore cheapness because it's wrong. We ignore it because it offends our taste. For a century, we trained ourselves to equate beauty with truth, smooth infinities, flawless symmetries, unlimited precision. Thrift feels like duct tape. That's an aesthetics bias, not an argument. Okay, so basically, 3 forces keep cheapness off stage: taste, incentives, and history. Start with taste. We celebrate the cathedrals, Maxwell's equations, Einstein's field equations, the elegance of Lorentz symmetry, while downplaying the scaffolding that made them usable: renormalization, effective theories, error budgets, and approximations that turned heroic math into reliable predictions. We love the marble, not the load-bearing beams. But beams are what keep the building standing. Incentives turn that bias into habit. Careers grow under big promises, not careful cost accounting. Revealing hidden dimensions outshines shaving 6 parameters with locality. Journals like Spectacle, grants reward novelty. Conference talks gravitate to fireworks over well-crafted nulls. Even our language betrays it. We say fine-tuned like an accusation, ugly like a verdict, approximation like an apology. In software, engineers brag when a simple patch saves 1 million CPU hours. In physics, we rename the patch and bury it in formalism. The math is honest, but the story we tell about it is. History keeps tapping our shoulder anyway. Renormalization looked like broom work in the 194s and 195s. Wilson's renormalization group in the 197s turned it into a deep organizing principle. Effective field theory once sounded like defeat. Now it's the gold standard for prediction under a cutoff. The standard model felt like a particle zoo. It outpredicted everything for decades. Lattice QCD was brute force. It delivered non-perturbative numbers we could trust. Over and over, thrift tools, locality, scaling, redundancy, carried the field while taste lagged behind. Microstory. A mentor once told me, you get rewarded for solving problems that look hard, not for the ones that are hard. The hard problems are often thrift problems. Which details can we safely ignore? Which invariants carry prediction? Where does a small spend buy a big gain? They look humble on a slide, but they're the moves that make deep theories useful, and they're the habits that keep mistakes from ballooning. Here's the weird part. Our resistance isn't just academic, it's personal. The universe is cheap can feel like a downgrade of human significance, as if living in a compressed, budgeted reality makes meaning thinner. So we reach for lush multiverses, exact supersymmetries, platonic landscapes, stories that flatter our appetite for perfection. But thrift doesn't shrink wonder, it concentrates it. Precision arising from harsh constraints is more astonishing, not less. 20 watts runs a mind. A handful of constants choreographs galaxies. That's all with receipts. Institutional risk reinforces the cover-up. It's safer to polish a lemma in your slice of the field than to stick your neck out with a cross-field synthesis like Spacetime is a code's ledger, or constants are coupled caps. Review panels fear being fooled by ambitious narratives. Early career scientists can't bet their future on an integrative story that spans quantum information, gravity, and cosmology. So we default to narrow wins. The result is a long tail of excellent local work, and a culture that struggles to fund the bridges. Nobody explains this right, but hype is a subsidy we quietly accept. We dress up incremental progress as revolution to get resources that careful, budget-aware science actually needs. Later we apologize when the breakthrough is a stronger bound or a cleaner null. The irony is painful. If we told the thrift story well, how constraints build reliability, how compression multiplies consequences, we'd have a narrative strong enough to fund itself without theater. Everything clicked for me when I noticed the same arc in other fields. Biology downgraded junk DNA, then discovered regulatory logic and thrift strategies everywhere. In machine learning, simple models with the right inductive bias beat deep networks in low data regimes. In economics, market designs that restrict degrees of freedom produce stability. Across domains, the pattern repeats. Constraints plus redundancy make systems workable at scale. So how do we surface cheapness without killing excitement? 3 moves. First, teach constraint as craft. Put information thermodynamics, effective field theory, and error correction in the core curriculum. Make what can we safely ignore a first-class question. Second, reward coordinated nulls. A family of linked limits that closes a theory space deserves as much spotlight as one flashy anomaly. Third, update our metaphors. Replace approximation as apology with the shortest program that reproduces the data within the caps. That's what elegance looks like under constraints. Microstory. A colleague once chased a beautiful signal exactly where a speculative model predicted a floor. Champagne chilled. 2 weeks later, ground loop from a cryocooler. The bump died. He didn't hide it. He published the veto and wrote the test into every future run. That's the culture we need. Predict shapes, pre-register expectations, build cross-lab vetoes so your instrument has to collude with the cosmos to fool you. Here's what this actually means for you. If you're a student, learn to love the beams, symmetries, locality, renormalization, error budgets. If you're a researcher, make your bets falsifiable and coupled across instruments. If you're a curious listener, ask for receipts. Which constants set this limit? Which invariants carry this prediction? Where do the floors bite? Cheapness isn't cynicism, it's discipline. It's how complex things survive under hard caps. The emotional payoff is simple. Embracing thrift doesn't make the universe smaller, it makes your map better. You trade grandiose fog for sharp edges you can test. And when the tests cut, you either uncover a subtle, coordinated floor, or you tighten the net so cleanly that new ideas have to be crisper to survive. Either way, you win. You get a world that's more legible, more reliable, and frankly, more worthy of your attention. So the cosmic energy lie wasn't that the universe deceives you. It's that we've been telling ourselves a story where beauty means boundless. The receipts say otherwise. Precision is paid, bandwidth is capped, storage is by area, and the render is on demand with error correction on top. That's not downgrading reality. That's the blueprint that lets you actually build with it. Here's what changed for me. I used to think cheap meant shabby, like the universe was running on duct tape and prayers. But the universe isn't shabby, it's optimized. Every constant, every cap, every noise floor is a feature that lets complexity survive under brutal constraints. Your 20-watt brain, the sun's fusion, the way galaxies cluster, all of it works because limits force elegance. That's not a downgrade of wonder. That's all with receipts. You thought reality was infinite. It isn't. And that's more beautiful. Key takeaway: reality runs like an optimized, low-resolution computation. Bits cost heat. Speed is capped by energy and C. Storage scales with area, and error correction keeps the render stable. If you want the next click to really land, watch our deep dive on how quantum error correcting codes literally reconstruct spacetime. Subscribe for more tested claims, not slogans, and drop one falsifiable pre-registered prediction you bet on. Then tell us how you'd break it.